The concept of continuity is very, very important in calculus and in physics and in most places. And so we want to talk about what does it mean to be continuous for a function. A function is said to be continuous at x at some point a if the limit as x goes to a of your function is actually equal to f of a. In other words, as I'm approaching a from both directions, my function is approaching f of a, whatever the function value is. And so first off, this definition gives you a couple ideas. First off is the function has to have a value there. In other words, you can't be driving along a road and suddenly have a hole. So you can't have that. The kind of think of it as this is a road you're driving along, and you want to be able to finish that road, not have a hole or pothole to drive into. So f of a has to be defined, has to have a value there. The limit has to also exist. So I can't, again, be driving along a road and have to go and jump up to get to this next part. I have to be able to continue along on my route. So there's no jumps, is kind of what you think of it as. The limit actually does exist. And then the third one is that the limit has to actually equal the function value. That's kind of the definition of continuity. And the three things together give you your definition of continuity, give you conditions. If any one of these three things is not true, then your function is what we call discontinuous. So let's take an example, a graphical example of where is this function discontinuous is actually what we care about. Because if you can find where it's discontinuous, you'll know it's continuous everywhere else. So the first thing I notice is there seems to be something going on at x equals 2. So let's see if we can figure out what's going on at x equals 2. So at x equals 2, there appears to be something going on, some reason why it's not continuous. When I'm coming along, the function f of 2 does in fact exist. It's right here, this dot right here means my function is defined at that point. But what I notice is the limit from the left and the limit from the right are not hitting the same value, so the limit does not exist. So x equals 2 is discontinuous because the limit as x goes to 2 of my function does not exist. So let's see if there's any other points. So there's another point here. There seems to be something weird going on here at x equals 5. So x equals 5 looks like another point where there's a point of discontinuity. Again, looking at this, my function, going back to your definition of continuity, the first condition is your function has to be defined. And I notice my function is defined. There's a dot right there. The second one is that the limit has to exist. So if I look at here, my limit from the left, my limit from the right are both heading towards the same value. So the limit does in fact exist. And the third condition is that the limit actually equals the function value. And now if I look here, my limit's heading to this y value, but my function's down here. So think of this as you're driving along some road and there's a pothole that needs to be filled and they filled the pothole somewhere different. That would be a problem. So here in this case, we would say that's discontinuous because the limit as x goes to 5, which does exist, and the function of f of 5, which does exist, is defined, do not equal each other. Let's go up and see if there's any other points. So now I look along and I see x equals 7 seems to have a problem. So x equals 7 is another point of discontinuity. Again, looking at those three conditions for being discontinuous or being continuous, my function has to be defined there. In other words, there has to be a dot there. If I look here, I notice I have an open dot. So therefore, my function is undefined. So we say f of 7 is undefined. And so that being the case means it's discontinuous there. Looking up here, I've got the x equals 2, x equals 5, x equals 7. I don't see any other places where there seems to be an issue. So these are the places of discontinuity. So let's just look a little bit more graphically at what this actually means. So I want to talk about what these values actually look like and mean in general. So looking at this, here's an example again of where we have a point of discontinuity. And the reason is that the function is undefined there. Oops. I'm going to actually say it a little bit differently. Instead of saying the function is undefined there, I'm going to say f of a is undefined. Now, the reason I call it undefined and not existing is because I could define it. I could make a piecewise function of this and say, I want to make f of a be a value, and I could make it be whatever this limit is. So that means that this is what we call removable, because I could, in fact, create a way to make this discontinuity point go away. So we call this removable because I could, in fact, make it be continuous by just defining my function to be some value. That's why we call this undefined, because I could define it to be something. Let's look at this one. Here, the limit goes up to infinity. The limit goes up to infinity. Even though they head towards the same value, we actually say the limit doesn't exist. It's infinity, but we actually say the limit doesn't exist. So in this case, the limit does not exist, and so that's why it's discontinuous. I can't remove this. I can't suddenly make this limit exist. I can't make suddenly have a value. So we don't call this removable because it's not. We actually call this an infinite discontinuity. There's nothing I can do about this one. It's going to be discontinuous. So this next one, again, it's a point of discontinuity because the limit as I'm heading towards a is heading towards whatever function value this is, but my function's up here. So in this case, this is said to be the limit as x goes to a of f of x does not equal f of a. Again, we could have fixed that. We can fix this one by just defining our function differently. So this again is called removable. This one, the limit from the left is heading, let's go at a, it's heading towards this value, this y value. The limit from the right is heading towards this y value, and the two y values are not the same. So we now can say this case, this one is the limit as x goes to a of f of x does not exist. And again, we can't fix this one. It's not that they're infinite, because these are not infinite, they just jump. So we call this one a jump discontinuity. All right. So f is said to be continuous from the right at x equals a if the limit from the right is equal to the function value. F is continuous from the left at a if the limit from the left is equal to the function value. So it's just another kind of way to think about what's happening. If you happen to have a function that stops at one place, you can talk about continuity still. A function f is continuous on an interval if it is continuous at every number in that interval. So instead of just saying we're continuous at a single point, we can actually say we're continuous over a much larger interval. And so when we look at the endpoints, we would look at continuous on the left and right at those endpoints. So let's do an example where we're going to show that f of x equals the square root of 1 minus x squared is continuous on the closed interval from -1 to 1. So let's first just look at being on the open interval. We're going to let a be in that open interval. We won't worry about the endpoints just yet. So we're going to let a be some number between -1 and 1, not including -1 and 1. So let's look at what the limit as x goes to a of that number is, of f of x, would be the limit as x goes to a of my function. Using my limit laws, I can take this as the square root of the limit of 1 minus x squared. And this would be the square root of 1 minus a squared, because I take this limit, and because of direct substitution, I can just plug that in. It's a nice polynomial. And then I notice, hey, that is what f of a is equal to. So I just showed that the limit as x goes to a of f of x is in fact equal to f of a. So therefore, f is continuous on -1 to 1. So all is good. So now what we do is we have to look at the actual endpoints. So let's see what happens at those actual endpoints. So at x equals 1, let's start with that one. That means we're looking at the limit as x goes to 1 from the left, because we're between -1 and 1. So we're coming up to 1, we're coming from the left of 1 minus x squared. Again, using our limit laws, this would be the limit as x goes to 1 from the left of 1 minus x squared, then square root of that limit. Direct substitution I can now use. So I can use direct substitution. I get 1 minus 1 squared, which is 0. Square root of 0 is 0. And f of 1 is 0. So that means we are continuous from the left at x equals 1. Now let's do the same thing going towards -1. So let's see what happens as x goes to -1. Then we're looking at the limit as x goes to -1, but now we're going to come from the right, because again, if you're on some interval from -1 to 1, you're going to be approaching from the right of 1 minus x squared. Again, using our limit laws, this would be the limit as x goes to -1 from the right of 1 minus x squared, square rooted. Again, using direct substitution, this is just 1 minus 1 squared, which is 0, and square root of 0 is 0, and this is f of -1. So we are continuous from the right. At x equals -1. So we've shown that we're continuous on the interval from -1 to 1 open. We've now shown we're continuous from the right, from the left at 1, and we now know we're continuous to the right at -1. So that means that f is continuous on -1 to 1 inclusive. Cool. All right, another theorem. This theorem says if f and g are continuous functions at a, and c is just some constant, then the following functions are also continuous. So f plus g would still be continuous. F minus g would still be continuous. Some constant times f would still be continuous. Multiplication of two functions would still be continuous. Division of the functions would be continuous provided that g of a is not 0. Let's go ahead and just do a quick little proof of one of these. So we're going to do a proof of f minus g is continuous. So using the definition of continuity, the limit as x goes to a of f of x minus g of x is what we want to find. Now we need to remember the supposition of the assumptions of this is that f and g are in fact continuous. So if f and g are in fact continuous, then that tells me that the limit as x goes to a of f of x is f of a, and the limit as x goes to a of g of x is g of a, because we know we're assuming that f and g are continuous. So we have these to work with. We're going to work with those. Again, we're going to use our limit laws. Our limit laws tell us that this limit of f of x minus g of x is the limit as x goes to a of f of x minus the limit as x goes to a of g of x. When we're trying to prove things in mathematics, a lot of times we start with one side that we're trying to go towards and head to the other. Usually we start with the more complicated side and try to head towards the simplest side. It doesn't always work this way, but this is a good idea. So we now have this limit that we're working with. And we now know that, remember, we're assuming that the f and g are continuous. So this limit as x goes to a of f of x is f of a. And the limit as x goes to a of g of x is g of a. Now we also know from our functions that we've been working with before that the subtraction of two functions is f minus g of whatever my x value is. And therefore I proved it's continuous. So I can now say, so f minus g is continuous because I've shown you that the limit of as x goes to a of fx minus g of x is f minus g of a. And that's the definition of continuity. Another theorem is that the following types of functions are continuous at every number in the domain. I'm not going to prove this to you, but this is something we can prove. Every polynomial is continuous. Every rational function is continuous in its domain. So if your domain is to exclude some numbers, then it's not continuous at those points, but they're not part of the domain, so it's okay. Any root function. So make sure that you've looked at the domain of your root function. Any trig function, again, looking at the domains. Any inverse trig functions, any exponentials, and any logs. So let's do a few examples of trying to find some of these. Let's find the limit as x goes to 4 of 3x squared minus 2x minus 1 over 4x plus 5. So because they're continuous, I can use the I can use the fact that if they're continuous, the limit should equal the function value. So let's just see what happens when I plug that in. So if I plug 4 in for x in the top, because continuity tells me that these will in fact be continuous, and I can plug in my function f. The limit should equal the function evaluated at 4. Let's see what happens when we do this. I get 4 squared, which is 16 times 3, which is something. I'm looking to see what it is because I can't remember what it is. All right, I'd have to figure it out. So let's go figure it out. So it actually would be, 55 is the numerator. And the bottom is 21. So that's the answer. There's your limit. Let's do another example of this. Let's find where the arctangent of x squared minus 4 over 3x squared minus 6x is continuous. So the first thing we need to look at is what is the domain of this? So let's look at x squared minus 4 over 3x squared minus 6x. That is continuous wherever your denominator is not 0. So find out where that's not 0. And that's not 0 when x is not 0 or 2. So that means that this is continuous everywhere except at 0, 2. Okay, so that's great, except we have a composition here. So we have to look at where the arctangent is continuous. And the arctangent is actually continuous in all real numbers. So that means that our function is continuous from -infinity to 0, 0 to 2, and then 2 to infinity. All right. Another theorem I just want to mention is that if G is continuous at A and F is continuous at G of A, then the composition is continuous at A. And we just kind of saw that. We know that these are all continuous there, and so everything's fine. So this is the introduction to continuity. There's more to this, but this is kind of the introduction I want you to see.